Welcome back. It's time to start a new unit. This is going to be a big change for us. We spent so many weeks on things like phase diagrams and intermolecular forces and aqueous solutions. It's good to make the change. Today, we're going to start off a new unit on chemical equilibrium and reversible reactions. And in starting, what I want to do in this video is just talk about the difference between the types of reactions that we're used to seeing so far this year, which are forward reactions, versus reactions that are reversible, can go in either what we call the forward or the reverse direction. Most of the reactions that we've studied this year have been forward reactions. We have a reactant like C right here on the left-hand side, and it eventually decomposes or reacts and turns into product like D here on the right hand side of that equation. We can assume that eventually the reaction, quote unquote, finishes as soon as we run out of C. So let's say that we had a starting point where we had 100 molecules of C and 0 molecules of D. And over time, we saw a change. And the change that we saw eventually resulted in the loss of all 100 molecules of C as they became 100 molecules of D. Now, I need to kind of pay attention to, my coefficients here, and because they're in a 1-to-1 ratio, my math is fine. But at the end of this process, you would eventually run out of C, and you would have 100 molecules of D, and the reaction's just over at that point. There's no going back. But a lot of reactions, especially reactions that take place within aqueous solution, turns out that they are reversible. The forward reaction, which we consider to be going from left to right, is sort of in a competition with what we are now introducing as a reverse reaction. In other words, that we are turning product back into reactant. So if you look over here on the right-hand side of our screen, we have A turning into B, but B can also turn into A. Hey, just for kind of traditional, what we're used to, we're going to still call A here our reactant, and B is going to be our product. But note that B can act like a reactant as it's turning back into A. So the math becomes a little bit more difficult. I'm not going to sketch out the same thing I did with C and D before, but you can imagine this. Let's say that we started again with 100 molecules of A and no molecules of B. Why is the math different now? Is there a time when A is going to reach 0? When the answer is no. Because as soon as we start to produce molecules of B, those molecules of B will go back and react to form A again. So I can never get to a point where I have 0 molecules of A if I started out with any in the first place. Likewise, you could imagine another scenario. This is just a second starting scenario. What if we started, on the other hand, with 0 molecules of A, and let's say we started with 100 molecules of B? How would that reaction start? It would proceed going back to the left in the reverse direction. So initially, what we would see is the reaction take place, and the amount of B would start to decrease as the amount of A started to increase. Okay, well, I'm still never going to get to a point where I get to 0 B. right? Because I started with some B, eventually I'm going to start making A, and that A is going to react to go back to B. A little bit confusing. So we're going to spend a lot of class today working on the math that is involved in thinking through what equilibrium really is and what equilibrium really is not. So let's get back together in our Google Meet just for a few minutes to talk about what's coming in our next video. And then we'll have an activity for you guys to kind of grapple with what it means to reach equilibrium. See you in a minute.